Hey guys, all right, next one I wanted to break down is the one you see here, 2010, B form, free response. And notice, most of these tend to be question one because the first question of the free response is very often an equilibrium question. All right, so if we take a look at this one, it tells us we have a compound, butane, C4H10, and it has two isomeric forms, what we call N-butane and isobutane. Both compounds exist as gases, all right, at those conditions. Draw me the structural formula for each of the isomers, including all the atoms, and clearly label each. Now, these days, you don't have to be able to name them, all right? Back when this was around in 2010, we had to do a bit of organic. You guys still need to be able to draw isomers, though. And remember, a structural isomer is a formula that can be drawn two different ways, but it's not resonance. We aren't moving double bonds around. We're moving atoms around to fundamentally create two different chemical compounds with two different distinctive set of properties. All right, so C4H10 is a hydrocarbon chain. The most common way to do hydrocarbon chains is to string all your carbons together in a straight line. And then you surround it with the hydrogens. Right? So there's one H, two H's, three H's, four H's, five H's, six H's, seven H's, eight H's, nine H's, 10 H's. Right? So there's one of my structural isomers. Right? You wouldn't know this, but this is the N-butane. N means it's one big long chain. Right? Now, what you have to start thinking is where could I move things around to create something that's different? So you can't just say, oh, pull this C and plug it here, because it'll still be the same chain. Right? If I pull this C and move it down here off this carbon, it's still the same. It's still 1, 2, 3. There. If you put it here, there'd be 4 carbons in a row surrounded. But the one that is different is if you move this carbon to the middle carbon, it's different because we won't get 4 carbons in a row at any point. That would create a structural isomer if we do this, right? Because now the most carbons in a row I can get is 3. 1, 2, 3. 1, 2, 3, 1, 2, 3. It is a different chemical compound because now we only have 3 carbons, which is a propane-based substance. All right, so we put our H's around, and don't be surprised. 3 H's, 4, 5, 6, 7, 8, 9. There's my 10. All right. Like I said, you guys don't need to be able to label which one is neobutane and which one is the propane-based one. All right? But you got to be able to draw them. All right, if we look into letter B, it says on the basis of molecular structure, identify the isomer that has the higher boiling point and justify your answer. All right, so this is a very common theme we see in chemistry. All right, they'll give you substances and ask you about their boiling points, their melting points, their vapor pressure, their surface tension, and all of those physical properties are controlled by intermolecular forces, IMFs. All right, so what we need to do is go through and check. So first thing we see, none of these are like covalent networks that would make it super duper strong. None of them are ionically bonded or metallic bonds, which would make them have immensely high physical properties. Both of these are hydrocarbons, which means fundamentally, you're only looking at covalent bonds. So you're looking at hydrogen bonding possibly, dipole-dipole, and London dispersion forces. So if you take a look, as we look at this, I take a look at this substance and this. They have the same formula, which means they have the same molar mass. So the whole idea of like more polarizable electron cloud, is in effect here. And one of the things you need to remember about the more polarizable electron cloud, is the longer the chain, the more polarizable. So you would want to say this substance has higher IMFs and boiling point because of a more polarizable electron cloud. All right, and that's due to it having a longer chain, right, as we go through those. All right, so if we head down to the next one, it says the two isomers exist in the, I'm sorry, it's easier to just read off my paper. Equilibrium with the N-butane and the isobutane. They give us that equation, and they give us the Kc value of that. And it says, suppose we put a 0.10 mole sample of it in a 1 liter container, and the first thing it wants us to do is write a K expression for this. Right? So again, K is always products over reactants to the power of the coefficients, but don't list solids and pure liquids. All right, so if we're looking at this guy, they're both gases. So I'm looking at the concentration, right, of isobutane to the first over the concentration of N-butane to the first. If they had given us pressures, this would have been a Kp. It would have been parentheses with a pressure isobutane, parentheses with a P butane. Just watch for those subtle differences. All right, then into D. They want us to get the initial pressure in the container when we first introduce the N-butane, so before the reaction occurs. All right, so I don't see anything in here, all right, listed, all right, about the pressure, all right, except for it says both compounds exist as a gas at 1 atmosphere, and that's the external pressure, so I can't really do much with that. So what I'm working with is I know the moles of it, I know the temperature of it, and I know the volume of it, right? And if I know those three things, I can do a PV equals nRT problem to get what the initial pressure is. Right? So if I solve that PV nRT problem, looking for my pressure, it's nRT over V. They told us our moles was 0.010. Your gas constant R is 0.0821 liters ATM per mole Kelvin. The temperature was 25. But remember, temp has to be in Kelvin when you use the 0821, and it's a 1 liter container. All right, so if we do the math on that, looks like we're going to get a value for the pressure of 0.24 atmospheres. And that's only going to carry 2 sig figs because the 0.010. All right, then you're into letter E. E says the N-butane reacts until the equilibrium has been established. Calculate the total pressure in the container at equilibrium. All right, so let me go ahead and list our equilibrium. Here we've got the N-butane in equilibrium with the isobutane. All right. Now, they're asking, calculate the total pressure in equilibrium. So you knew your initial pressure was what we got right back here. All right, the 0.24 atmospheres. All right, and I don't actually have to do a math problem for this one, right? Because if you look at this, I have 1 mole of N-butane for 1 mole of isobutane. All right, so every time an N-butane goes away, which was a gas, I create an isobutane, which replaces it, which is a gas. That means I'm going to have the same number of molecules, whether I'm at equilibrium or at the beginning. They may be different molecules, but I will have the same total number. That means my pressure is not going to change. So it's going to be 0.24 atmospheres, because it is a 1-to-1 ratio of gas molecules. All right. Now, they want the molar concentration at equilibrium for each species. That we do have to get a number for. Okay, right? Because we're at equilibrium, we need to do an ice table. All right, so we knew our initial concentration of the N2-butene was 0.010 molar. Why was it that? Well, it was 0.010 moles, and we had a 1 liter container. We didn't have any isobutane to begin with. That means my equilibrium is going to shift toward the 0, so minus x plus x. That makes this 0.010 minus x and x. Then you'd plug into your K expression. Right? K is going to be equal to x over 0.010 minus x. We know the K value from the equation up above. It listed it as 2.5. Right, so if I want the equilibrium concentrations of both of these, I need to solve this guy for x. Right, so if we go ahead and do that, no crazy math there. Right, x is going to be 2.5 times 0.010 minus the x. Right, distribute there. So our 2.5 times our 0.010 is 0.025 minus 2.5x. Swing that to the other side. Looks like 3.5x is equal to 0.025. Solving for x. You get a value of 0.0071 mole. Sometimes x is your answer, sometimes it's not. They want the equilibrium concentration of each species. So there's one of my answers because the isobutane is x. Right? So my isobutane is equal to 0.0071 molar, but my N-butane has a math problem involved. So the N-butane is going to be the 0.010 minus the 0.0071. Right, and if we do that math, you're going to get a value of 0.0029. All right. And there's your molar concentration of each. Question 3 of that E. It says, if I cut the volume of the system in half, what will be the new concentration of the N-butane after the equilibrium reestablishes? Right, so if I cut the volume in half, right, in theory, what it's going to do is double the molarity. Right? But think of this from a Le Chatelier's point of view. We were at equilibrium, and then I cut the volume in half. So that would increase the pressure. The system is going to shift to decrease the pressure. But look, you're a 1-to-1 ratio. It can't do anything to fight that. So if you manipulate the volume, what's going to be the new concentration of the N-butane after the equilibrium reestablished? It is going to be the same as it was whether we did that or not. All right, so for number 3, like I said, if you cut the volume in half, you're going to double the concentration, and there's going to be no shifting. All right, so what you're going to do, is simply take 2 times the 0.00298, or sorry, 0029 that you got there. All right, so just trying to figure out where I can squeeze that in. Stay right here. So if you cut the volume in half, means 2 times the molarity. And that whole thing I was talking about with the whole shifting is cutting the volume in half does that to the molarity. But if the equilibrium can reduce some of my pressure, it would shift again. You'd have to do a different ice table. But you don't need to do that because it's the 1-to-1 ratio. All right, so I didn't want you to think the molarity is the same. It does double the molarity, but it's going to not be able to do anything after it does that. And then last but not least, the Letter F says calculate the molar concentration of each species after equilibrium has been reestablished. And this time it started with the 0.010 over here. It will do the same thing. When you reach equilibrium, no matter which direction you start from, you are going to get the same result, right? Because if I put the 0.010 here, this would be my minus x, my plus x. I would end up doing the same math like down below. And when I did that, I would get the same numeric values for my equilibriums. All right, so your answers for letter F are going to be exactly the same as they were right here, 0.0071 and 0.0029. I hope this helps you guys out. More videos to come.